Hey everyone, welcome to PLA Academy. Hope you found this video useful. If you did, it'd be awesome if you could subscribe, like the video, share it with your friends, and maybe drop a comment. Your support really helps me make more videos. In this video, I covered everything on the syllabus, like you can see in the figure. Principle of superposition. Superposition is the principle that when waves of the same type meet at a point, their individual displacements combine to produce a resultant displacement. As a blue wave travels to the left and a red wave travels to the right. Initially, they are in phase, meaning their phase difference is zero. When these waves meet, their individual displacements combine constructively, resulting in a maximum resultant displacement that is twice the amplitude of either individual wave. This is called constructive superposition, which occurs when waves are in phase, with phase differences of 0 degree, creating the maximum amplitude. When a blue wave travels one division to the left and a red wave travels one division to the right, their individual displacements combine to create the resultant displacement, as shown. When a blue wave travels one division to the left and a red wave travels one division to the right, the phase difference between two waves is pi radians, or 180 degrees, they are said to be in antiphase. Their individual displacements combine destructively, resulting in a minimum resultant displacement, which can be zero if the waves have equal amplitudes. This is called destructive superposition, which occurs when waves are in antiphase, with phase differences of pi radians, or 180 degree, creating the zero amplitude. When a blue wave travels one division to the left and a red wave travels one division to the right, their individual displacements combine to create the resultant displacement, as shown. When a blue wave travels one division to the left and a red wave travels one division to the right, the phase difference between two waves is 2 pi radians, or 360 degrees, they are said to be in phase. Their individual displacements combine constructively, resulting in a maximum resultant displacement that is twice the amplitude of either individual wave. This is called constructive superposition, which occurs when waves are in phase, with phase differences of 2 pi radians, or 360 degrees, creating the maximum amplitude. Therefore, we can be concluded that the constructive superposition, which occurs when waves are in phase, with phase differences of 0, 2 pi, 4 pi, 6 pi, and so on. The destructive superposition, which occurs when waves are antiphase, with phase differences of pi, 3 pi, 5 pi, 7 pi, and so on. Exam-style question 1. The three waves shown in each diagram have the same amplitude and frequency, but different phase. They are added together to give a resultant wave. In which case is the resultant wave zero at this instant? In a choice A, there are three waves as blue, violet, and green coolers, like this. At this point, displacements of three waves combine to be zero, like this. At this point, displacements of three waves combine to be zero, like this. At this point, displacements of three waves combine to be zero, like this. And any positions the resultant displacements of three waves combined together to become zero, like this. So, A is correct. Stationary wave. Stationary waves, or standing waves, are formed by the superposition or interference of two progressive waves traveling in opposite directions with the same frequency, wavelength, and speed. This interference results in a pattern of nodes and antinodes. At nodes are the destructive superposition. Their phase differences are pi, 3 pi, 5 pi, 7 pi, and so on. Or 180 degrees, 540 degrees, 900 degrees, 1260 degrees, and so on. Their path differences are lambda over 2, 3 lambda over 2, 5 lambda over 2, 7 lambda over 2, and so on. At antinodes are the constructive superposition. Their phase differences are 0, 2 pi, 4 pi, 6 pi, and so on. Or 0 degrees, 360 degrees, 720 degrees, 1080 degrees, and so on. Their path differences are 0, lambda, 2 lambda, 3 lambda, and so on. When a blue wave travels to the right and a red wave travels to the left, as shown, they are moving in opposite directions and they have same frequency, wavelength, and speed. At the initial, they are in phase, and phase difference is 0. They superpose, or interfere, with each other to create the stationary wave shown in black wave. After 1/8 of a period, each wave travels 1/8 of a wavelength in opposite directions, resulting in a separation of 1/4 of a wavelength. They superpose to form the stationary wave shown in black wave. After 1/4 of a period, each wave travels 1/4 of a wavelength in opposite directions, resulting in a separation of half a wavelength. They superpose to form the stationary wave shown in black wave. After 3/8 of a period, each wave travels 3/8 of a wavelength in opposite directions, resulting in a 3/4 wavelength in separation. They superpose to form the stationary wave shown in black wave. After half of period, each wave travels half a wavelength in opposite directions, resulting in a full wavelength separation. They superpose to form the stationary wave shown in black wave. When two waves traveling at high speeds in opposite directions superpose, they can form stationary waves, which appear as a series of loops, as shown. This creates a pattern of nodes and antinodes, as shown. At nodes, the amplitude is at minimum. In this diagram, it is 0 because the waves have equal amplitudes. At antinodes, the amplitude is maximum. The distance between two loops is equal to wavelength lambda. So, the distance between consecutive nodes or antinodes are half of the wavelength. Exam style question 2. The diagram shows a sketch of a wave pattern over a short period of time. Which description of this wave is correct? In the diagram shown the stationary wave, the distance for two loops is a wavelength. For 1 meter has 5 loops, which is equivalent to 2.5 wavelengths. So, we can determine the wavelength of the wave is equal to 1 meter divided by 2.5, which is 0.4 meters, or 40 centimeters. The transverse waves and longitudinal waves can be occurred the stationary wave. In the choice A, the wave is longitudinal, has a wavelength of 20 centimeters and is stationary. This is incorrect. In the choice B, the wave is transverse, has a wavelength of 20 centimeters and is stationary. This is incorrect. In the choice C, the wave is transverse, has a wavelength of 40 centimeters and is progressive. This is incorrect. In the choice D, the wave is transverse, has a wavelength of 40 centimeters and is stationary. This is correct. Stationary wave of the stretched string. A vibrator generates an incident wave that travels to the left. This wave reflects at the pulley, creating a reflected wave traveling to the right. The incident and reflected waves have the same frequency, wavelength, and speed. These two waves superpose to produce a standing wave. The simplest standing wave pattern, with a single loop, is called the fundamental frequency, or the first harmonic. The fixed ends at the vibrator and pulley are always formed nodes, because the string cannot free to vibrate. The vibrator varies the frequency until a stationary wave with 2 loops, second harmonic, 3 loops, third harmonic, 4 loops, fourth harmonic, and so on. Let L be the length of the stretched string. Recall that 2 loops of stationary wave equals 1 wavelength. For first harmonic has a single loop, indicating that L equals half of wavelength, so the wavelength equals 2L. The fundamental frequency, F1, can be calculated by dividing the speed v by wavelength, lambda. Substituting lambda equals 2L. So, F1 equals V over 2L. 4-second harmonic has two loops, indicating that L equals wavelength, lambda. The second harmonic frequency F2 is calculated by dividing the speed v by wavelength, lambda. Substituting lambda equals L. So, F2 equals V over L, or 2V over 2L. And V over 2L equals F1. So, F2 is twice as F1. 4-third harmonic has three loops, indicating that L equals 3 lambda over 2, so lambda equals 2L over 3. The third harmonic frequency F3 is calculated by dividing the speed v by wavelength, lambda. Substituting lambda equals 2L over 3. So, F3 equals 3V over 2L. And V over 2L equals F1. So, F3 is 3 times of F1. 4-fourth harmonic has four loops, indicating that L equals 2 lambda, so lambda equals L over 2. The fourth harmonic frequency F3 is calculated by dividing the speed v by wavelength, lambda. Substituting lambda equals L over 2. So, F4 equals 2V over L or 4V over 2L. And V over 2L equals F1. So, F4 is 4th times of F1. Exam style question 3. A stationary wave is produced on a string that is stretched between two fixed points that are a distance of 1.35 meters apart, as shown. The speed of the waves on the string is 450 meters per second. What is the frequency of oscillation of the stationary wave? The standing wave has three loops, which corresponds to 1.5 wavelengths. So, 1.35 meters equals 1.5 wavelengths. This means one wavelength is 1.35 meters divided by 1.5 is equal to 0.9 meters. The frequency of the stationary wave can be calculated by the equation F equals V over lambda. Substituting V equals 450 meters per second and lambda equals 0.9 meters. We get the frequency equals 500 Hz. So, C is correct. The stationary wave of sound wave in air column with closed one end. A speaker generates an incident sound wave that travels through a pipe closed at one end. This wave reflects at the closed end, creating a reflected wave traveling in the opposite direction. The incident and reflected waves have the same frequency, wavelength and speed. The superposition of these two waves can produce a standing wave. The simplest standing wave, with a quarter-loop pattern, is called the fundamental wave, or the first harmonic. This corresponds to the lowest frequency that can be heard, hence the term fundamental frequency. A closed end of the pipe forms a node, because air particles cannot vibrate freely. An open end forms an antinode, because air particles can vibrate freely. The speaker varies the frequency until a stationary wave with second heard, second harmonic, 3 heard, third harmonic, and so on. Let L be the length of the air column. Recall that two loops of stationary wave equals one wavelength. For first harmonic has an 1/4 loop pattern, indicating that L equals 1/4 of a wavelength, so the wavelength equals 4L. The fundamental frequency F1 can be calculated by dividing the speed v by wavelength, lambda. Substituting lambda equals 4L. So, F1 equals V over 4L. 4-second harmonic has a 3/4 loop pattern, indicating that L equals 3/4 of a wavelength, so the wavelength equals 4L over 3. The second harmonic frequency F2 can be calculated by dividing the speed v by wavelength, lambda. Substituting lambda equals 4L over 3. So, F2 equals 3V over 4L. And V over 4L equals F1. So, F2 equals 3 times of F1. 4/3 harmonic has a 5/4 loop pattern, indicating that L equals 5/4 of a wavelength, so the wavelength equals 4L. The third harmonic frequency F3 can be calculated by dividing the speed v by wavelength lambda. Substituting lambda equals 4L over 5. So, F3 equals 5v over 4L. And v over 4L equals F1. So F3 equals 5 times of F1. Exam style question 4. A long glass tube is almost completely immersed in a large tank of water. A tuning fork is struck and held just above the open end of the tube as it is slowly raised. A louder sound is first heard when the height h of the end of the tube above the water is 18.8 centimeters. A louder sound is next heard when h is 56.4 centimeters. The speed of sound in air is 330 meters per second. What is the frequency of the sound produced by the tuning fork? The first heard when h is 18.8 centimeters. The next heard when h is 56.4 centimeters. So, half of wavelength equals 56.4 minus 18.8 is equal to 37.6 centimeters. Therefore, 1 wavelength equals 2 times 37.6 is equal to 0.752 meters. The frequency can be calculated using the equation F equals V divided by lambda. Substituting V equals 330 meters per second and lambda equals 0.752 meters. We get the frequency F equals 440 Hz for two significant figures. So, B is correct. The stationary wave of sound wave in air column with open both ends. A speaker generates an incident sound wave that travels through an open pipe. This wave reflects at the open end, creating a reflected wave traveling in the opposite direction. The incident and reflected waves have the same frequency, wavelength and speed. The superposition of these two waves can produce a standing wave. The simplest standing wave, with one loop pattern, is called the fundamental wave, or the first harmonic. This corresponds to the lowest frequency that can be heard, hence the term fundamental frequency. Both open ends forms an antinode, because air particles can vibrate freely. The speaker varies the frequency until a stationary wave with second heard, second harmonic, 3 heard, third harmonic, and so on. Let L be the length of the air column. Recall that 2 loops of stationary wave equals 1 wavelength. For first harmonic has an 1 loop pattern, indicating that L equals half of a wavelength, so the wavelength equals 2L. The fundamental frequency F1 can be calculated by dividing the speed v by wavelength lambda. Substituting lambda equals 2L. So, F1 equals V over 2L. For second harmonic has a 2 loops pattern, indicating that L equals 1 wavelength. The second harmonic frequency F2 can be calculated by dividing the speed v by wavelength lambda. Substituting lambda equals L. So, F2 equals V over L, or 2V over 2L. And V over 2L equals F1. So, F2 equals 2 times of F1. 4/3 harmonic has a 3/2 loops pattern, indicating that L equals 3/2 of a wavelength, so the wavelength equals 2L over 3. The third harmonic frequency F3 can be calculated by dividing the speed v by wavelength lambda. Substituting lambda equals 2L over 3. So, F3 equals 3V over 2L. And V over 2L equals F1. So, F3 equals 3 times of F1. Exam style question 5. Stationary sound waves can be formed in the air columns of pipes. One type of pipe is closed at one end and open at the other end. Another of pipe is open at both ends. Which pipe can form a stationary sound wave with the lowest frequency? Let V represent the speed of sound in air. Choice A. Consider a pipe open at both ends. The lowest frequency, or fundamental frequency, standing wave has a half wavelength pattern, 1 loop, is shown. 1 loop is equivalent to half wavelength. So, 2L equals a half of lambda. And lambda equals 4L. Using the equation, the frequency F equals speed V over wavelength lambda. Substituting lambda equals 4L. So, F equals 0.25 V over L. Choice B. Consider a pipe is closed at one end. The lowest frequency, or fundamental frequency, standing wave has a quarter wavelength pattern, half loop, is shown. A half loop is equivalent to quarter wavelength. So, 2L equals 1/4 lambda. And lambda equals 8L. Using the equation, the frequency F equals speed V over wavelength lambda. Substituting lambda equals 8L. So, F equals 0.125 V over L. Choice C. Consider a pipe open at both ends. The lowest frequency, or fundamental frequency, standing wave has a half wavelength pattern, 1 loop, is shown. 1 loop is equivalent to half wavelength. So, L equals a half of lambda. And lambda equals 2L. Using the equation, the frequency F equals speed V over wavelength lambda. Substituting lambda equals 2L. So, F equals 0.5 V over L. Choice D. Consider a pipe is closed at one end. The lowest frequency, or fundamental frequency, standing wave has a quarter wavelength pattern, half loop, is shown. A half loop is equivalent to quarter wavelength. So, L equals 1/4 lambda. And lambda equals 4L. Using the equation, the frequency F equals speed V over wavelength lambda. Substituting lambda equals 4L. So, F equals 0.25 V over L. So, B has the lowest frequency. Stationary wave of microwave. An incident microwave traveling toward a metal reflector is reflected and travels in the opposite direction. The incident and reflected waves have the same frequency, wavelength, and speed. The superposition of the incident and reflected microwaves creates a stationary wave pattern with nodes and antinodes. A detector measures the microwave signal intensity of microwave. This detector can be used to locate the nodes and antinodes of this standing wave by moving the detector between the microwave source and the reflector. The alternating points of minimum and maximum signal intensity can be observed. The points of minimum signal intensity correspond to the nodes. The points of maximum signal intensity correspond to the antinodes. The distance between successive nodes or antinodes is equal to half of a wavelength. Exam-style question 6. In an experiment to demonstrate a stationary wave, two microwave transmitters, emitting waves of wavelength 4 centimeters, are set facing each other, as shown. A detector is moved along a straight line between the transmitters. It detects positions of maximum and minimum signal. The detector is a distance d from the left-hand transmitter. Assume that both transmitters are at antinodes of the stationary wave. Which row gives a value of d for a maximum and for a minimum? At the maximum signals is the antinodes. At the minimum signals is the nodes. The question given the wavelength of microwave is 4 centimeters, so half of a wavelength is 2 centimeters. The distance between consecutive antinodes or nodes is 2 centimeters. And the distance between consecutive antinodes and nodes is 1 centimeters. From the diagram, shows that the value of d for a maximum signals or antinodes occur to be 0, 2, 4, 6, 8, and so on, which are even numbers. The value of d for minimum signals or nodes occur to be 1, 3, 5, 7, and so on, which are odd numbers. So, the value of d for a maximum can be 46 and 48 centimeters. The value of d for a minimum can be 47 centimeters. So, C is correct. Difference between the stationary wave and the progressive wave. The progressive wave can be transferred the energy from one place to another. The progressive wave transfers the energy in this direction. The stationary wave cannot be transferred the energy from one place to another. However, the energy is stored in the vibrating particles, like this. All the points along the progressive wave have the same amplitude. This amplitude is the maximum displacement that all point in wave can be oscillated. The stationary wave has the amplitude of different point to vary from a maximum to 0. The 0 amplitude is at nodes. The maximum amplitude is at antinodes. All the points over one wavelength in progressive wave have different phases. All the points between successive nodes are in phase. For example, all points in same color section have phase difference is 0. All points in pink and yellow regions have phase difference equals 360 degrees, which is also in phase. All points in red and yellow regions have phase difference equals 720 degrees, which is also in phase. All points in blue and yellow regions have phase difference equals 180 degrees, which is antiphase. All points in green and yellow regions have phase difference equals 540 degrees, which is antiphase. Exam style question 7. Which statement concerning a stationary wave is correct? Choice A. All the particles between two adjacent nodes oscillate in phase. This is correct. Choice B. The amplitude of the stationary wave is equal to the amplitude of one of the waves creating it. This is incorrect. The amplitude of a standing wave varies from 0 at the nodes to a maximum, which can be twice the amplitude of the individual waves at the antinodes. Choice C. The wavelength of the stationary wave is equal to the separation of two adjacent nodes. This is incorrect. The distance between two adjacent nodes is half a wavelength. Choice D. There is no displacement of a particle at an antinode at any time. This is incorrect. At antinodes, its displacement is maximum, while no displacement at nodes. Hey everyone, welcome to PLA Academy. Hope you found this video useful. If you did, it'd be awesome if you could subscribe, like the video, share it with your friends, and maybe drop a comment. Your support really helps me make more videos. In this video, I covered everything on the syllabus, like you can see in the figure. Diffraction of wave. Diffraction is the spreading out of a wave as it passes through a narrow gap, aperture, or around an obstacle. The amount of diffraction depends on the wavelength of the wave compared with the size of the gap, aperture, or the size of the obstacle. When straight wave fronts encounter a gap, or aperture, in a barrier, they pass through and diffract, spreading out into the region beyond. The wave fronts curve at the edges of the gap, while the central portion remains relatively straight. This shown that these area are diffracted. This area is not diffracted. As the size gap decreases to approach the wavelength, diffraction becomes more, resulting in greater spreading and curvature of the wave fronts, as shown. As the size gap decreases to very smaller than the wavelength, diffraction increases, resulting in greater spreading and curvature of the wave fronts, but the diffraction pattern may become less distinct, as shown. So, we can conclude as follows. When the aperture is much larger than the wavelength, diffraction is minimal, little waveform's curvature. When the aperture size is comparable to the wavelength, diffraction increases, greater curvature of wave fronts. When the aperture is much smaller than the wavelength, diffraction is significant, but the diffraction pattern may become less distinct. When a wave encounters an obstacle, diffraction occurs around the edges. When straight wavefronts with a wavelength much smaller than the width of the obstacle, diffraction is minimal, resulting in slight curvature of the wavefronts at the edges as shown. This creates a shadow region behind the obstacle where the wave is blocked. As wavelength increases, diffraction increases, leading to greater curvature of the wavefronts at the edges as shown. This results in a less distinct, or no shadow region behind the obstacle, as the wave bends around it. When a sound wave passes through a doorway, the size of the doorway is comparable to the wavelength of the sound, causing the diffraction to occur. When light passes through a doorway, the size of the doorway is typically much larger than the wavelength of light, resulting in no diffraction. To investigate the diffraction of the visible light using a single slit. The slit width should be less than approximately 10⁻⁻⁴ meters, or 0.1 millimeters. This is because the wavelength of visible light ranges from about 10⁻⁻⁶ to 10⁻⁻⁷ meters. When monochromatic light from a laser source passes through a single slit, it diffracts, as shown. The central fringe of the diffraction pattern has the highest intensity and greatest width. Decreasing the slit width increases diffraction, leading to greater spreading of the light and a decrease in intensity. This increased diffraction also results in a wider central fringe. The diffraction pattern of white light through a single slit is shown. The central fringe is white, while the other fringes display a spectrum of colors, with blue light closer to the center and red light further away. This occurs because red light has a longer wavelength than blue light, and longer wavelengths diffract more, spread out more. The diffraction patterns of red, green, and blue light through a single slit are also shown. The red light's central fringe is the widest, while the blue light's central fringe is the narrowest. This is consistent with red light's longer wavelength, which causes greater diffraction than green or blue light. To investigate the diffraction of water waves using a single slit in a ripple tank. The wavefronts of waves are generated using a vibrating bar, and move towards a gap in a barrier. Where the ripples strike the barrier, they are reflected back. Where they arrive at the gap, however, they pass through and spread out into the space beyond. It is this spreading out of waves as they travel through a gap, or past the edge of a barrier. A ripple tank is a shallow tray of water with a light source shining down through it. The light illuminates the wavefronts, making them visible. A straight dipper can be used to create straight wavefronts in a ripple tank. When the dipper is vibrated up and down, it creates a series of parallel wavefronts passing through a gap. To observe the diffraction of the water wave on a screen, the stroboscope, or video camera, is used to make the slow motion of the wavefronts of water wave on the screen. Exam style question 1. The speed of sound in air is 330 meters per second. Which size of architectural features in a large concert hall would best diffract sound waves of frequency 0.44 kHz? The size of architecture features should be comparable to wavelength of the sound waves, resulting in the best diffraction. So, we can calculate the wavelength of the sound first using the equation. Wavelength lambda equals speed v over frequency f. Substituting v equals 330 meters per second, and f equals 0.44 times 10 power 3 Hz. We get the wavelength lambda equals 0.75 meters, or 750 millimeters. So, the size of architecture features should be 750 millimeters. Exam style question 2. In an experiment, water waves in a ripple tank are incident on a gap, as shown. Some diffraction of the water waves is observed. Which change to the experiment would provide a better demonstration of diffraction? The best diffraction occurs when the size of gap is comparable to the wavelength. Choice A, increase the amplitude of the waves. This is incorrect, because the amplitude does not affect diffraction. Choice B, increase the frequency of the waves. This is incorrect, because increasing the frequency decreases the wavelength, which would reduce diffraction. Choice C, increase the wavelength of the waves. This is correct, because increasing the wavelength makes it closer to the gap size, leading to more diffraction. Choice D, increase the width of the gap. This is incorrect, because increasing the gap width decreases the amount of diffraction. Hey everyone, welcome to PLA Academy. Hope you found this video useful. If you did, it'd be awesome if you could subscribe, like the video, share it with your friends, and maybe drop a comment. Your support really helps me make more videos. In this video, I covered everything on the syllabus, like you can see in the figure. Interference of wave. Interference occurs when two coherent waves meet at a point. They superpose, producing a pattern of nodes and antinodes. At the antinodes have the phase differences to be 0, 2 pi, 4 pi, 6 pi, and so on. Or 0, 360 degrees, 720 degrees, and so on. And their patch differences are 0, lambda, 2 lambda, 3 lambda, and so on. At the nodes have the phase differences to be pi, 3 pi, 5 pi, 7 pi, and so on. Or 180 degrees, 540 degrees, 900 degrees, and so on. And their patch differences are half a lambda, 3 half lambda, 5 half lambda, and so on. Waves are considered coherent when they satisfy the following conditions. They have a constant phase difference. This is the most important condition. They are the same type of wave. They have the same frequency and wavelength. For example, green and blue waves are coherent. This is because both waves maintain a constant phase difference of 180 degrees, and they have the same frequency and wavelength. Their amplitude are not equal, but do not affect coherence. Pink and blue waves are coherent. This is because both waves maintain a constant phase difference of 90 degrees, and they have the same frequency and wavelength. Their amplitude are not equal, but do not affect coherence. Red and green waves are not coherent. This is because they do not maintain a constant phase difference, and do not have the same frequency or wavelength. To investigate the interference of water waves in the ripple tank. Two dippers connected to the same oscillator vibrate with the same frequency, generating two coherent water waves. When the bar vibrates, each dipper acts as a source of circular ripples spreading outwards. Where these sets of ripples overlap, an interference pattern is projected onto the screen below. This interference pattern is visible on the screen. The pattern consists of alternating regions of constructive and destructive interference. Along this line are locations of destructive interference, resulting in nodes. Along this line are locations of constructive interference, resulting in antinodes. Along this line are locations of destructive interference, resulting in nodes. Along this line are locations of constructive interference, resulting in antinodes. Along this line are locations of destructive interference, resulting in nodes. Along this line are locations of constructive interference, resulting in antinodes. Along this line are locations of destructive interference, resulting in nodes. Another way to observe interference in a ripple tank is to use plane waves passing through two gaps in a barrier. The water waves are diffracted at the gaps and then interfere beyond, creating a similar pattern. The interference pattern in the ripple tank. Two sources S1 and S2 produce coherent waves, with a phase difference of 0. The waves have the same wavelength lambda. Given the red line represents the crest, and green line represents the trough. Along the yellow lines are locations of constructive interference, resulting in antinodes. These points are formed the superposition of wave crests with crests, or wave troughs with troughs. Along this black lines are locations of destructive interference, resulting in nodes. These points are formed the superposition of wave crests with troughs. Recall that, at the nodes have the phase differences to be pi, 3 pi, 5 pi, 7 pi and so on. Or 180 degrees, 540 degrees, 900 degrees, and so on. And their patch differences are half a lambda, 3 half lambda, 5 half lambda, and so on. At the antinodes have the phase differences to be 0, 2 pi, 4 pi, 6 pi, and so on. Or 0, 360 degrees, 720 degrees, and so on. And their patch differences are 0, lambda, 2 lambda, 3 lambda, and so on. The difference in distance from any point along black and yellow lines to sources S1 and S2 respectively is the path difference for that line. The central yellow line marks the zero-order antinode A0. At this antinode, both the path difference and the phase difference are 0. This means that the distance from any point on this line to the two sources, S1 and S2, is equal. For example, at point A on this line, the distance S1 to A is 5 lambda, and the distance S2 to A is also 5 lambda. At the left next black line marks the first-order node N1. At this node, the path difference is half a wavelength and the phase difference are 180 degrees. This means that the difference in distance from any point on this line to the two sources, S1 and S2, is half a wavelength. For example, at point B on this line, the distance S1 to B is 5 lambda, and the distance S2 to B is also 5.5 lambda. At the next yellow line marks the first-order antinode A1. At this antinode, the path difference is 1 wavelength and the phase difference are 360 degrees. This means that the difference in distance from any point on this line to the two sources, S1 and S2, is 1 wavelength. For example, at point C on this line, the distance S1 to C is 4.5 lambda, and the distance S2 to C is also 5.5 lambda. At the next black line marks the second-order node N2. At this node, the path difference is 3 half wavelength, and the phase difference are 540 degrees. This means that the difference in distance from any point on this line to the two sources, S1 and S2, is 3 half wavelength. For example, at point D on this line, the distance S1 to D is 3 lambda, and the distance S2 to D is also 4.5 lambda. At the next yellow line marks the second-order antinode A2. At this antinode, the path difference is 2 wavelength and the phase difference are 720 degrees. This means that the difference in distance from any point on this line to the two sources, S1 and S2, is 2 wavelength. For example, at point E on this line, the distance S1 to E is 4 lambda, and the distance S2 to E is also 6 lambda. At the next black line marks the third-order node N3. At this node, the path difference is 5 half wavelength and the phase difference are 900 degrees. This means that the difference in distance from any point on this line to the two sources, S1 and S2, is 5 half wavelength. For example, at point F on this line, the distance S1 to F is 3 lambda, and the distance S2 to F is also 5.5 lambda. At the next yellow line marks the third-order antinode A3. At this antinode, the path difference is 3 wavelength and the phase difference are 1080 degrees. This means that the difference in distance from any point on this line to the two sources, S1 and S2, is 3 wavelength. For example, at point G on this line, the distance S1 to G is 2.5 lambda, and the distance S2 to G is also 5.5 lambda. This pattern is symmetric about the central yellow line, like this. Exam style question 1. Two sources of microwaves P and Q produce coherent waves, with a phase difference of 180 degrees. The waves have the same wavelength lambda. At the point S, there is a minimum in the interference pattern produced by waves from the two sources. The distance, QS minus PS, is called the path difference. Which expression could represent the path difference? At the initial, the waves from sources P and Q have phase difference of 180 degrees, so the path difference between two waves is half a wavelength. The path difference for minimum interferences at point S can be 1/2 lambda, 3/2 lambda, 5/2 lambda, and so on. The half lambda path difference from the sources adds to any path difference to determine the overall path difference at point S. Choice A, the overall path difference equals 1/4 lambda plus 1/2 lambda equals 3/4 lambda. This is incorrect. Choice B, the overall path difference equals 1/2 lambda plus 1/2 lambda equals 1 lambda. This is incorrect. Choice C, the overall path difference equals 1 lambda plus 1/2 lambda equals 3/2 lambda. This is correct. Choice D, the overall path difference equals 3/2 lambda plus 1/2 lambda equals 2 lambda. This is incorrect. Exam style question 2. An outdoor concert has two large speakers beside the stage for broadcasting music. In order to test the speakers, they are made to emit sound of the same wavelength and the same amplitude. The curved lines in the diagram represent wave fronts. Where is the loudest sound heard? The wave fronts connect points of equal phase in the sound wave, such as compressions. The loudest sound occurs where constructive interference takes place. Constructive interference happens when compressions from both speakers overlap, or when rarefactions from both speakers overlap. This occurs where the wave fronts from the two speakers intersect. So, D is correct. Investigating the interference of sound waves. Two identical loudspeakers, connected to a single generator, produce coherent sound waves with a phase difference of 0. As a microphone is moved along line AB in front of the loudspeakers, a series of alternating loud and quiet regions is observed. At the loud regions, constructive interference occurs, resulting in a sound intensity that is twice that of a single loudspeaker. These regions are called antinodes. At the quiet regions, destructive interference occurs, resulting in a sound intensity that is lower than that of a single loudspeaker. These regions are called nodes. The central loud region marks the zero-order antinode. At this antinode, both the path difference and the phase difference are 0. At the next quiet region marks the first-order node. At this node, the path difference is half a wavelength and the phase difference are pi radians. At the next loud region marks the first-order antinode. At this antinode, the path difference is 1 wavelength and the phase difference are 2 pi radians. At the next quiet region marks the second-order node. At this node, the path difference is 3/2 wavelength and the phase difference are 3 pi radians. This pattern is symmetric about the central quiet, like this. The graph shows the variation of sound intensity detected by the microphone with distance from point A, as displayed on the CRO. The intensity at nodes may not be exactly 0 due to the presence of background noise. Exam style question 3. Two loudspeakers are placed near to each other and facing in the same direction. A microphone connected to an oscilloscope is moved along a line some distance away from the loudspeakers, as shown. Which statement about the waves emitted by the loudspeakers is not a necessary condition for the microphone to detect a fixed point along the line where there is no sound. Choice A. The waves must be emitted in phase. This is not a necessary, because the interference can be occurred if the waves emitted in out of phase. Choice B. The waves must be emitted with a similar amplitude. This is a necessary, because we need to detect where no sound, which means that completely destructive interference. Choice C. The waves must have the same frequency. This is necessary, because it is condition of coherent waves. Choice D. The waves must have the same wavelength. This is necessary, because it is condition of coherent waves. Investigating the interference of light waves. A white light source is used, rather than a laser. A monochromatic filter allows only one wavelength of light to pass through. A single slit diffracts the light. This diffracted light arrives in phase at the double slit, which ensures that the two parts of the double slit behave as coherent sources of light. The double slit is placed a centimeter, or two beyond the single slit, acts as two coherent sources. The interference pattern is observed on a screen about a meter away. The bright fringes have equal intensity and are equally fringes separation, as shown. The experiment has to be carried out in a darkened room, as the intensity of the light is low and the fringes are hard to see. When a red filter is used, an interference pattern is shown. When a green filter is used, an interference pattern is shown, showing that the fringe separation is smaller than with red light. When a blue filter is used, an interference pattern is shown, showing that the fringe separation is smaller than with green light. When no filter, the interference pattern of white light is shown. This pattern shows a spectrum cooler, with blue light fringes closer to the center, and red light fringes further away. This is because red light has a longer wavelength than blue light, and longer wavelengths diffract more, spread out more. Three key factors influence the experimental setup. Slit width. Slit widths are typically a fraction of a millimeter. Since visible light wavelengths are much smaller, minimal diffraction occurs, allowing for sufficient light intensity to observe fringes. Narrower slits would significantly reduce light intensity. Slit separation. Double slits are usually separated by about a millimeter. Larger separations would result in closely spaced fringes, making them difficult to distinguish. Screen distance. The screen is placed approximately 1 meter from the slits. This distance provides clearly separated fringes without excessive dimming of the light. Exam style question 4. Light of wavelength lambda is incident normally on two narrow slits S1 and S2, a small distance apart. Bright and dark fringes are observed on a screen a long distance away from the slits. The N dark fringe from the central bright fringe is observed at point P on the screen. Which equation is correct for all positive values of N? All positive values of N equals 1, 2, 3, 4, and so on. The dark fringes occur where destructive interference take place, which happens when the path differences are 1/2 lambda, 3/2 lambda, 5/2 lambda, and so on. Choice A. The path differences are 1/2 lambda, lambda, 3/2 lambda, and so on. This is incorrect. Choice B. The path differences are lambda, 2 lambda, 3 lambda, and so on. This is incorrect. Choice C. The path differences are 1/2 lambda, 3/2 lambda, 5/2 lambda, and so on. This is correct. Choice D. The path differences are 3/2 lambda, 5/2 lambda, 7/2 lambda, and so on. This is incorrect. Young's double slit experiment. A laser produces intense coherent light. As the light passes through the double slits, it is diffracted, spreading out into the space beyond. This creates two overlapping sets of waves, and an interference pattern is observed on a screen placed about a meter away. We will focus on the interference pattern within this specific region. Within this region, the bright fringes exhibit equal intensity and consistent fringe separation as shown. The double slit experiment can be used to determine the wavelength, lambda of light. The following three quantities have to be measured. Slit separation, A in meters. Fringe separation, X in meters. This is the distance between the centers of adjacent bright, or dark, fringes. Slit to screen distance, D in meters. The formula for calculating the wavelength is lambda equals AX divided by D. This formula can explain why the fringe separation for red light is greater than that for green and blue light, as shown in the diagram. Given a constant slit separation A and slit to screen distance D, the wavelength lambda is directly proportional to the fringe separation X. Since red light has the longest wavelength, the fringe separation X for red light is greatest. Blue light, with the shortest wavelength, exhibits the smallest fringe separation. Exam style question 5. A double slit interference experiment is set up as shown. Fringes are formed on the screen. The distance between successive bright fringes is found to be 4 mm. Given the wavelength of red light equals lambda, the slit separation equals A, the slit to screen distance equals D, and fringe separation X equals 4 mm, as shown in the diagram. Two changes are then made to the experimental arrangement. The double slit is replaced by another double slit, which has half the spacing. The screen is moved so that its distance from the double slit is twice as great. What is now the distance between successive bright fringes? From the equation, lambda equals AX divided by D. Rearranging the equation as X equals lambda D divided by A. From the diagram, the old fringe separation X equals 4 mm. Substituting new D equals 2D, and new A equals A over 2. So, new X equals 4 lambda D over A. Substituting lambda D over A equals 4 mm. So, new X equals 16 mm. Exam style question 6. The diagram shows an arrangement for demonstrating two-source interference using coherent light of a single wavelength lambda. An interference pattern is observed on a screen 3.0 meters away from the slits X and Y, which have a separation of 1.0 millimeters. The central bright fringe is at Q, and the second bright fringe from the center is at P. What is the distance between Q and P? The distance PQ equals 2x. From the equation, lambda equals AX divided by D. Rearranging the equation as X equals lambda D divided by A. Substituting D equals 3 meters, and A equals 1.0 times 10 power negative 3 meters. We get the fringe separation X equals 3 times 10 power 3 lambda. So, 2x equals 6 times 10 power 3 lambda. Hey everyone, welcome to PLA Academy. Hope you found this video useful. If you did, it'd be awesome if you could subscribe, like the video, share it with your friends, and maybe drop a comment. Your support really helps me make more videos. In this video, I covered everything on the syllabus, like you can see in the figure. Diffraction grating. A diffraction grating consists of a large number of equally spaced lines ruled onto a glass or plastic slide. Each line acts as a source of diffraction for the incident light. The gratings can have up to 10,000 lines per centimeter. When light passes through the grating, an interference pattern of fringes is observed. In the diagram, monochromatic light from a laser is incident normally on a transmission diffraction grating. Beyond the grating, interference fringes are formed and can be observed on a screen, similar to the double-slit experiment. The fringes are also referred to as maxima. The central fringe is called the zeroth-order maximum A0. The next fringe is the first-order maximum A1. The next fringe is the second-order maximum A2, and so on. The pattern is symmetrical, so there are two first-order maxima A1, two second-order maxima A2, and so on, as shown. To analyze the pattern, we measure the angles theta and beta at which the maxima are formed, rather than measuring their separation. With double slits, the fringes are equally spaced and the angles are very small. With a diffraction grating, the angles are much greater, and the fringes are not equally spaced. The differences in the interference patterns between diffraction gratings and double slits are as follows. Brighter and sharper fringes. Diffraction gratings typically produce brighter and sharper fringes than double slits, because more light passes through the numerous slits in the grating. Larger fringe separation. Diffraction gratings generally exhibit larger fringe separations than double slits, because the slit spacing in gratings is much smaller than the slit separation in typical double-slit experiments. The wavelength lambda can be determined with a diffraction grating. By measuring the angles at which the maxima occur, we can determine the wavelength of the incident light and calculating using the equation d sin theta equals n lambda. Where d is the grating spacing in meters, theta is the angle between the zero-order maximum and n-order maximum, n is the order of maximum as 1, 2, 3, and so on, and lambda is the wavelength of light in meters. If the grating has k lines per meter, then the grating spacing d can be calculated using d equals 1 divided by k. Exam style question 1. A beam of red laser light of wavelength 633 nanometers is incident normally on a diffraction grating with 600 lines per millimeters. The beam of red light is now replaced by a beam of blue laser light of wavelength 445 nanometers. A replacement diffraction grating is used so that the first-order maximum of the blue light appears at the same position on the screen as the first-order maximum of the red light from the original laser. This means that the angle theta is the same for both, and the first order corresponds n equals 1. How many lines per millimeter are there in the replacement diffraction grating? Using the equation d sin theta equals n lambda. For the blue light and the replacement grating, we have d2 sin theta equals 1 time blue lambda. For the red light and the original grating, we have d1 sin theta equals 1 times red lambda. Dividing the first equation by the second equation, we get d2 sin theta over d1 sin theta equals blue lambda over red lambda. So, sin theta is the same for both, it cancels out, leaving d2 over d1 equals blue lambda over red lambda. Substituting blue lambda 445 nanometers, and red lambda equals 633 nanometers. The nanometers cancel out, so we get d2 equals 445 over 633 times d1. Substituting d2 equals 1 over k2, and d1 equals 1 over k1. Where k2 and k1 are the number of line per millimeters for the replacement and original gratings, respectively. Substituting k1 equals 600 per millimeters. We solve k2 equals 850 per millimeters for two significant figures. Exam style question 2. Monochromatic light of wavelength 690 nanometers passes through a diffraction grating with 300 lines per millimeters, producing a series of maxima, bright spots, on a screen. What is the greatest number of maxima that can be observed? The diffraction grating with 300 lines per millimeters So grating spacing D equals 1 over 300 millimeters, or 1 over 300 times 10 power negative 3 meters. Using the equation d sine theta equals n lambda. Substituting d equals 1 over 300 power negative 3 meters, theta equals 90 degrees, and lambda equals 690 times 10 power negative 9 meters. We solve for n order maxima equals 4.83, but n must be a whole numbers, so the maximum order is 4. So, the greatest number of maxima that can be observed is 4 plus 1 plus 4 is equal to 9 maxima, which includes the 0th order maximum and 4 maxima on left and right hand sides, as shown. We substitute the angle theta equals 90 degrees, because this represents the maximum possible angle from the 0th order maximum to the highest order maximum. I hope you found this video helpful. If you did, I would be grateful if you would subscribe, share, like and leave a positive comment. Your support will encourage me to create more content. Thank you.